Yeah, good morning, everyone, and welcome to today's advertising session. But don't you worry, you won't be pestered by nasty ads here. The only advertising we'll be having here today is for all these amazing papers that we're having in this session. And starting out will be Adam Silfen. He's from Google, and he'll be presenting not just one, but two papers. And the first one is called Summary Reports Optimization in the Privacy Sandbox Attribution Reporting API. So the stage is yours.
Thank you. So this is joint work with a bunch of my colleagues at Google, Hidayat Aksu, Badi Ghazi, Pratish Kamath, Ravi Kumar, Pasan Manurangsi, and Avinash Varadarajan. So the topic of this talk is ad conversion measurement. So in the advertising ecosystem, a user interacts with an ad on a publisher website, such as New York Times, Facebook, Google, any site that displays ads. And then the user performs some other actions, browses the web, and at some point, maybe the user converts on the advertiser's website, which means performs some desirable action from the perspective of the advertiser. It could be making a purchase, signing up for a newsletter, making an account, any action that the advertiser defines as a desirable action that they want to measure. And our goal is to understand what is the value of the ad. So join the ad interactions with the conversions to measure the real-world value of each ad. Now, traditionally, this was done using third-party cookies, which have major privacy concerns because they allow tracking of user behavior through the web. And user behavior can also be revealed from released statistics or ML models, or less fine-grained information than third-party cookies. But the measurement goals of advertising are aligned with privacy. The goal of an advertiser is to figure out how to run an ad campaign, what kinds of ad campaigns will bring in how much revenue. It shouldn't be tied to the behavior of a single user. It's about understanding patterns of large numbers of users, and we want it to be not too sensitive to outliers, to individual user behavior. So as a goal, this is actually quite compatible with privacy. There's many different ways of thinking about privacy. The formal model that I'm going to be using in this talk, although we're not going to get into any sort of mathematical details about it, is differential privacy, which is a widely used notion of privacy that assumes a very strong adversary, and it gets worst case guarantees about how much an adversary can learn about individuals in the data set. And it has a lot of nice properties like accounting of privacy loss over many computations, over many interactions. And typically the way differential privacy is achieved is there's a query you want to measure, and so instead of releasing the exact value, you release some kind of noised value where noise from some carefully chosen distribution is added to the query. So that's all I'm going to say about differential privacy formally, but there's been a lot of recent deployments both in industry and in government and in other areas. So Chrome and Android measurement APIs. So Google is producing APIs to replace third-party cookies for ads measurement on web and mobile, to be able to give accurate analytics about understanding the value of ads without the tracking behavior of third-party cookies. So there are two APIs, the event level API, which gives noisy event level data, and the aggregate API, which gives information about aggregates of data types. And because the data is aggregated, you're able to estimate sort of more rich information about conversion types. And sort of how much noise gets added depends on how large the aggregation is. So if you're sort of the coarser the category, the better the signal is compared to the noise. So we're interested in relating impressions and conversions. So you have user behavior on a publisher website, and then you have user interaction with ads later. So we're going to get into I'm going to get into this more in the next talk actually, but basically the aggregate API performs the linking between an impression and a conversion in the browser on device. And then you can think about this data set of this joined data set of impressions and conversions that has a combination of impression features and conversion features. And the goal is for each combination of impression features, for each maybe campaign and ad campaign and city, we want to report some information about the conversions that correspond to that ad campaign. Maybe the total number of conversions, the number of items that were purchased, the total price of the items purchased, things like this, while preserving privacy. And in the aggregate API, this is released through the API summary reports. And the summary reports are sort of a general tool. There's different ways to set it up. But this is sort of the general process is you can configure it with a set of aggregation keys that correspond to the metrics you're interested in measuring. So for instance, you could have an aggregation key for each combination of campaign and city, each combination of impression features you're interested in, and each metric you're interested in measuring. So the total price of all purchases this week in Bristol. And then for each attributed conversion, so you basically think of conversions as contributing a vector of length number of these aggregation keys, number of these buckets that we're computing. So each attributed conversion is encoded as a non-negative vector that corresponds to how much is being contributed to each of these quantities we're measuring. And then we want to estimate, the sum of this vector. But we need to make sure that sort of the noise hides individual contributions. So we need to cap the total contribution of any individual. So in the API, there's a fixed cap of 2 to the 16. And the total contribution, the total contributions of all of the potentially many conversions corresponding to an impression is capped at this value, 2 to the 16. And then these vectors, these histogram contributions are added up, and noise is added to each coordinate of the vector to satisfy differential privacy. And then you can take this noisy vector, and you can extract the individual, you can sort of look at the entries and use them to reconstruct estimates of the different values you're interested in, like the number of conversions in a particular place and time, or the different values that you want to measure. And so there's like two parts of this pipeline. The part in green is the part that's fixed by the API. So these are the algorithms that the API runs. The total contributions are capped, they're summed up, and noise is added. And that guarantees privacy. But choosing the aggregation keys, how to encode conversions as histogram contributions, and how to reconstruct the values are all up to the user. So for the same set of queries you're interested in, there's many ways to set this up, and there are trade-offs between the choices you can make here. So you basically, the total contributions are capped at this value gamma, 2 to the 16, but that can be divided however you like among the different queries that you're asking. There's multiple queries. There's also the range of possible values for each query. If purchases are on the scale, of a very large number, you want, like if you expect purchases to be small, you want to sort of scale them up to encode them as a large amount, so the noise is less impactful. But if the conversions are large, then you want to sort of have enough in your contribution budget to capture the range of values. And you also need to divide the budget among the multiple conversions for each impression. So you can think of this as like splitting the privacy budget among multiple queries. But basically what this means is that when we use the API, we need to specify for every query we want to measure, we need to specify the fraction of the total contribution budget that's going to be used for that query, and the maximum contribution for that query that we want to be able to record. And different choices for these parameters can lead to different accuracy under the same privacy guarantee. So our approach is to sort of write down. So given historical data, we can choose parameters that we can write down the error of a particular choice of parameters, and then we can run standard optimization libraries to choose these parameters. So this is simple and simple to implement and can be applied to any error metric, and we evaluated it on 4 data sets and several different error metrics. And what we found is that this sort of error approach, we compared it to a baseline that used a static quantile and an even budget and an even split of the contribution budget among the different queries, and we found that sort of for our baseline, some did better and some did worse in different regimes. But if you use optimization, unsurprisingly, you sort of beat the static. You get better accuracy than the static approaches, sort of across the data sets and parameter regimes. And for some of the error metrics, you get and data sets, you get a very large improvement. Although part of this is that's when the baselines do very poorly. So I think you shouldn't read too much into the sort of exact improvement numbers. But the take home here is that sort of not doing an optimization can perform pretty badly for some data sets and privacy budgets, but using optimization does well across the board. And it's sort of one question I want to highlight for future work is without access to historical data, how can we optimize budgets? How can we optimize these parameters? We took a first step in this direction by modeling synthetic data distribution. So one approach would be to try to use synthetic data, but there's a lot more work to be done. Now I think I'm out of time, so do we have time for 1 or 2 questions? Or?
I think we have time for one quick question. Yeah.
A couple of quick questions. One is related to, as you were describing these trade-offs, I understand that you're trying to optimize these parameters to improve utility, but there must be a trade-off, right? You're probably giving up some privacy. So how do you account and quantify that? And second related implementation question is, in the diagram that you were showing right here, is it my understanding correct that these attribution contributions, these reports are directly going to the server infrastructure of attribution reporting API?
Thanks for the question. For the first part, it's actually there's not a trade-off with privacy. So different settings of the parameters get the same privacy guarantee. So you're enforcing that at most the total contribution of 2 to the 16 is enforced. So that always satisfies the same differential privacy guarantee. The difference is that sort of among different queries, like the total privacy is the same, but for individual queries you might have more or less privacy and more or less accuracy. So it's a question of balancing the privacy across the different queries, so that even though the overall privacy is the same, you get the best possible accuracy for that level of privacy. For the second question, yes, the central part of the algorithm is run through this API. But sort of the algorithms A and R at the 2 ends get to be run by, like the user gets to define them. So it's configurable in that way.
I also got a very quick one. You just said the A&R algorithms are configurable by the ad tech, if I read that correctly. So how would that work in practice? So say I'm an ad tech platform and now I want to run this algorithm. So how would this work in practice? How do I communicate with the API? And where are these A&R algorithms implemented?
So I guess you have access to, thanks for the question. So when you get a conversion, you get to sort of record what you care about in that conversion, and you record that as a vector, and then you send that vector to the API. So it's a question of how you encode the vector, and then once you receive back the noisy aggregated vector, how do you decode that into the values you care about?
Okay, yeah, cool, thank you. Let's thank Adam again, and then welcome
Thanks
him
very much.
again for the next presentation, which is called Differentially Private Ad Conversion Measurement.
So I should first say this is not my work. The speakers weren't able to attend, so I'm presenting on behalf of John Delaney, Buddy Ghazi, Charlie Harrison, Christina Ilventa, Ravi Kumar, Pasim Manarangsi, Martin Pal, Karthik Prabhakar, and Mariana Raikova. So sort of the setup is going to start out very similarly. Where the topic is ad conversion measurement. A user visits a publisher website, interacts with an ad, and at some point later may convert on the advertiser website by making a purchase. And the goal is to understand the value of ads by joining these interactions. But now we're going to look at the ecosystem more as a whole. So a user may visit many publisher websites, interact with many ads, and then at some point later convert on the advertiser website, and it's not so clear which ad led to the conversion, if any, and how to attribute that. So sort of the goals are the same: to understand conversion rates, measure ad spend, bid in real time, optimize purchases of ad impressions, and so on. But now we want to understand the ecosystem more as a whole. So I'm going to sort of skip over that because it's very similar to what we just talked about. But release statistics or trained ML models can potentially reveal information about individual users. So we want to protect privacy, but that's compatible with our goals because ad campaigns shouldn't overfit to individuals. But the question is, what privacy notion should we actually use for ad conversion measurement? The framework is again going to be differential privacy. But that's actually not specific enough. There's many ways to use differential privacy and to apply it to ad conversion measurement. In particular, this is sort of getting at a few of the thorny details you have to deal with in practice. So in particular, when you have an input, so you have interactions, you have this input data set of ad interactions and ad conversions, then in order to limit the so in order to use this data set, we're first running this attribution system that's going to link up impressions with conversions. And then we're going to take this attributed data set and add noise to it. But the input we actually have is a sequence of ad interactions and conversions. So we want to make sure that this is end-to-end private, including the logic of the attribution system. But sort of to step back and look at the system, so each ad interaction consists of a bunch of different information about, maybe a timestamp, information about the publisher, advertiser, user, what type of interaction with the ad, whether it was a click or a view. And then the conversion might consist of, timestamp, IDs, and what type of conversion happened, or what the value of the conversion was, what the price of the purchase was. So this attribution system takes in a sequence of impressions and conversions, and returns sort of how to returns a estimate of which impression was responsible for that conversion. So there's a bunch of different approaches that are used. Some of the simplest are last touch attribution, where we assume that the most recent interaction with an ad was the one that drove the conversion, or first touch, where we assume it was the first. You can also look at a uniform where you give sort of partial credit to many different impressions, there's various different ways to apportion, to attribute in different ways. But what we want to make sure is that so the sequence of impressions and conversions is then mapped to a real vector by a low sensitivity function, and then we add noise distributed from an appropriate distribution to satisfy differential privacy. But sort of the question we have to settle is, what is the information we're actually trying to hide? We need to add like the differential privacy adds noise to mask some type of information about what went on. But this could be a single interaction. It could be a single conversion and all the impressions that correspond to one conversion. It could be all interactions of a user on a single publisher website, or all interactions of a user with a single advertiser, or all combinations, or at the sort of strongest type of privacy, we can ask to hide all interactions of a single user with all advertisers and all publishers and all conversions. And this is the strongest guarantee and requires adding the largest amount of noise, because you're trying to hide a lot of information in the system at the same time. So for whichever notion of privacy unit we choose, we need to limit the contributions of that type of information to ensure that the function has bounded sensitivity, so that we can add noise scaled to the maximum contribution that a change of this type can induce. So for each of these scopes, we can cap contributions to some maximum amount per that scope. So there's two ways we can envision doing this capping. We can cap for the input data set, where we can say, we know, for example, if we're doing user-level privacy, we're saying we're only going to record the first K actions of a particular user, and then we've consumed the privacy budget. We're going to ignore all future interactions. Or you can attribute, or you can cap after attribution, where you can say, maybe if you're doing sort of a user cross publisher notion of privacy, then you might get a sort of, once you've done attribution, you might see that the scope you might be able to sort of throw out fewer interactions. So sort of the downside of pre-attribution capping is that you can use up a budget on impressions and on impressions that don't end up mattering to later conversions. So you sort of you can end up adding more noise than necessary. But as we'll see, capping post-attribution is fairly tricky from a privacy perspective. So here's an example. We can do last touch attribution. So we can set this up in many ways. One choice would be to use last touch attribution with user cross publisher privacy unit or adjacency relation with post-attribution capping. So if we have a large advertiser campaign with ads displayed on many publishers, we might hope that since the privacy unit we've chosen is user cross publisher, if we're looking at the total number of ad interactions per publisher, the units per publisher, the function we want to compute is per publisher. It has sensitivity, constant sensitivity. We could hope for a private algorithm with error 1/epsilon. But this is actually not possible for this configuration, because since we're doing last touch attribution, adding new interactions with one publisher can remove all attributed conversions to all other publishers. So sort of a single change to one publisher can change all of the different values that you're computing for the other publishers. So there could be a lot of information leakage, and it would violate privacy to do post-attribution capping in this way, in this setting, unless we scale the noise with the number of publishers, which can be extremely large. So this would give poor utility in this setting. This work gives a so we can define a combination of adjacency relation, capping point, and attribution logic as valid if applying a cap of R ensures that the attributed data sets have distance roughly R in a way that doesn't depend on the number of publishers or advertisers. And the authors show that that for any combination, for any configuration that's valid, then adding noise scaled to the sensitivity of the function is overall differentially private, taking into account both the attribution logic and the rest of the system. So the paper classifies for each choice of privacy unit and attribution logic which combinations are valid and which combinations are invalid. So for pre-attribution capping, everything is valid, everything is private, but potentially some utility is left on the table. For post-attribution capping, it's a much more complicated story. Depending on the exact choice of attribution logic and the exact choice of privacy unit, some combinations are valid and some are invalid. And for some it depends on, there are some families of attribution logics where it depends on which member of the family we choose. Those are the orange boxes. So to conclude, we're assuming here that the privacy unit is the same as the unit at which we cap. This one could also look at a more general problem where that's not the case. We're also assuming here that you can cap in any way. There's also, this is a distributed, complicated system. There's also a question of how do you actually perform capping, whether you use secure multi-party computation or trusted execution enclaves or some other way. There's also this paper looked at the sort of most widely used simple ways of doing attribution, but there's also many other types of attribution one can consider, like data-driven attribution. And then also there's incentive questions with, if I pretend to be two different publishers, can I gain an advantage in this system? So there's a lot of questions of that flavor that one can ask.
Yeah, thanks again, Adam.
Thank you.
Do we have any questions? Yeah.
Thank you. So you have now shown two complex systems that you built around preserving privacy. And my general question is always, is it worth building these complex systems to still enable user tracking, or would it just not suffice to have a less complex system which is also less expensive that serves ads based on content a user sees?
That's a good question. I guess my interpretation would be that the reason these systems are being built is that it's deemed to generate enough revenue to make it worth it. But you can certainly imagine a system where static content is. If you look at, say, television advertising, you don't get to do this. You have to serve static. You have to serve ads, the same ads to everyone. And I think it does end up being sort of very different. It's useful to be able to do some kind of more sophisticated targeting, and so sort of finding the right trade-off between not doing tracking, but being able to sort of serve relevant ads, I think does end up being very useful.
Okay, thanks.
Here, let me do a more targeted follow-up to that. I think we are not suggesting that there should not be targeting. So let's imagine you're using topics API, use certain parameters to target ads. But why do we need to do conversion tracking in the browser? If I'm an advertiser, I'm running campaigns. Let's suppose one campaign is run using certain topics parameters, the other campaign with some other parameters. I can just have like different URLs to distinguish between the attribution conversion outcomes across different campaigns. Aggregation is naturally happening, and there is no need to do any conversion tracking in the browser. Why is that a bad idea?
So I guess my guess would be that that covers some use cases, but not others. So if you're only looking at conversions that happen when the user clicks through on the ad and then makes an immediate purchase on the website, then you can give a different link for different ad campaigns, and you can see whether this link came through your ad on Google or your ad on Facebook. But maybe the user sees an ad, and then the next day they're like, I really did want to buy a toaster. Let me go and buy this toaster that I saw. You're not going to get that with different links. So it depends. I mean, that can definitely do some of this, but probably not everything. Also, I guess there's a limit to how many different URLs you want to create. There's sort of trade-offs between what kind of information you can get from that. But it's certainly something one could do.
Okay, let's thank Adam again for his 2 amazing talks.
Thanks very much.